Hi, so today we are starting a series of videos on perturbation theory for quantum mechanics. Well, what is perturbation theory? Well, it is just another method that we have in order to solve the Schrödinger equation and to get the eigenenergies and eigenstates of the Hamiltonian of our system. So, just as a quick recap, let's say that we have some quantum system, and this quantum system is described by a Hamiltonian H. Then, what we usually need to do is to solve what we call the time-independent Schrödinger equation. And once we solve this equation, which is actually an eigenvalue problem, we can get the energy of the system, the energy levels, and the eigenstates of the Hamiltonian, which, if it is non-degenerate, constitutes a basis of our Hilbert space. But we'll get on with we'll get on with that afterwards. So the problem is that we have a Hamiltonian. And of course, we can just say, okay, let's just try to solve this problem. But the thing is that usually this problem is not easy to solve, and in fact, most times it cannot be solved analytically. So what do? Well, we say, okay, what if our Hamiltonian can be split into an H0 term, which we will be calling the unperturbed Hamiltonian. Okay, this is the unperturbed Hamiltonian, and another term that we're gonna call W, and this is called the perturbation. Well, in this case, we can solve it if this perturbation is really small and we know how to solve H0. That is, in principle, we cannot solve this problem with all of this, with this full Hamiltonian, because it is too hard. But if we do know this solution, okay, so if we know the solution for H0, and we don't have to know it for W, just for H0, then we can solve the problem as long as W is a lot smaller than H0. Okay, so we're assuming that we have a system with which we actually know. We have a lot of details and probably we know a lot of properties about the system because we can solve its eigenstate equation, and we introduce some perturbation W, which is quite small compared to our original energies. So what can be an example of this? For example, let's say that we have our hydrogen atom, which we don't know how to solve analytically, and we introduce an electric field that is not too strong, or a magnetic field. Then, of course, the system is not the same as before introducing the electric field, but if the electric field or magnetic field is sufficiently small, then we can use this method to calculate the corrections. That's what we call. So why do we call it corrections? Well, if initially we had this and it gave us these energies, this n just stands for the different energy levels, and this 0 for the energy of the system that we do know how to solve, then we initially have, but these are the energies. But if we introduce this perturbation, then, okay, so remember, our full Hamiltonian is the sum of these two terms. Then if we introduce this perturbation, the energies are no longer going to be En0, they're going to be En0 plus some corrections due to this new factor. So what we will do in perturbation theory is to see what is the form of these corrections, when can we actually apply perturbation theory, and how to get some knowledge, some information of the system, even if we don't know how to solve it analytically. So there are, of course, different cases for perturbation theory, and that's why we're going to be making a series of videos. So this video will not be too long and not too hard to follow. So we will divide it into a lot of different cases. Actually, there are really two main cases. And the first main case is where the Hamiltonian does not depend on time. That is, it is time independent. When Hamiltonian is time independent, we divide perturbation theory in two cases, degenerate and non-degenerate cases. We'll explain later on what this means. And there's another case where we have some time dependency in the Hamiltonian. This case is a bit harder, and what we usually do is we assume that the time dependency is given by this. We have an unusual time independent H0 term, and the time dependency is given in the perturbation. This would be analogous to applying a magnetic field that depends on time. For example, we turn it on at some time, and then we turn it off, or we vary it with some frequency or whatever we have. We just have that this W depends on time. Of course, as always, it is relatively small related to H0. So first of all, we'll be treating time-independent theory, which is really useful, and then we'll get on to understanding what time-dependent theory is. For now, let's just worry about this. So time-independent theory. We will consider two cases. Okay, as always, let me just write the form of a Hamiltonian. The difference between degenerate, let me just call this first of all non-degenerate, and degenerate perturbation theory comes only relative to H0. That is, let's say that we have H0 and we have our eigenvalue problem. And we know how to solve it. We know all the eigenvalues. We know, for example, E1 or E2, or it doesn't even have to be 1, 2, or so on. In general, we know what the form of En is, and we know what the corresponding eigenstate is. Okay, what this means, let me just write an N here. What this means is that in our system, if our system is in this state, it will necessarily have to have this energy. And if it is in another state, it will not have this energy, it will have a different energy. So this is what we call non-degenerate perturbation theory, or non-degenerate system. Non-degenerate only means that for each energy, we can only have one state. If we have, for example, this, that both of these states, which are different in general, have the same energy, we will no longer be dealing with non-degenerate perturbation theory. There will be a degeneracy, as we call it. And degeneracy is just a fancy word to say that, hey, there are two guys with the same energy. As a quick example to see what a non-degenerate system would be, let's just consider the harmonic oscillator. We know that this choice just means harmonic oscillator. We know that for the harmonic oscillator, the energies are given by this expression for the quantum harmonic oscillator, where n is 0, 1, 2, and so on. So these are all our energies. Notice that for each n, we have different energies. For for 0, we have 1/2 h omega. For 1, we have 3/2 h omega, and so on, so on, so on. And I'm not going to be doing it here because we will lose some time. I'll do it in other videos. But we know that the solutions or the eigenstates only depend on n. Okay, so for each different value of n, we get a different eigenvalue. For example, phi1 is not equal to phi2, okay? And E1 is not equal to E2 and so on. So for each n, we have a different energy and different eigenvalue. This means is that, for example, for the first energy, we only have one state with this energy, phi1. For the second energy, we only have another state, phi2 with this energy, and so on and so on. Okay, so I know I'm repeating myself a lot, but it's just so important to understand it from the beginning, because later on we're going to do it a bit more abstractly, and you can get confused with it. So just have to count that non-degenerate means that for each energy there's only one eigenstate, one state without energy. Now, regarding notation, because this is the nth energy level, in general it doesn't have to have this form. This n is just a quick notation to identify the energy level, but it could be n, m, or even have more than one subindex. So when we have the nth energy level, we're going to write an n in the eigenstate of Hamiltonian. And because we are dealing only with the unperturbed Hamiltonian, H naught, remember that our goal is to deal with all of this, but first of all we're distinguishing the case where we have general, non-degenerate, and degenerate. So for H naught, we're going to write this 0 right here. Okay, so this notation just means eigenstate of the nth energy for this Hamiltonian, H naught Hamiltonian. Now, what is the general perturbation theory? Well, let's consider the hydrogen atom. For the hydrogen atom, the energies are given by this expression. Okay, where E1 is just one constant, usually I think it's minus 13.56 electron volts or whatever. Doesn't really matter to us right now. It will in all problems, but not now. And we get that n goes from 1 to and so on. So in this case, of course, for each different value of n, the energy is different, but the eigenstates are not different. Our eigenstates are don't only depend on n, this n, they also depend on L, ML, S, and MS. They depend on 5 quantum numbers. So what does this mean? Well, let's say that I have n equals to 2. Then, of course, my energy can only be E2, which is E1 over 4. Now, is there only one eigenstate? Well, let's see. We have phi 2, but what is L? Usually, it's not the point of this video, but L is going from 0, 1, and so on, up to n minus 1. In our case, L can either be 0 or 1. So for n equals to 2, L is 0 or 1. So we already see that when we have n equals to 2, there's an ambiguity because we don't know if we want L equals to 0 or L equals to 1. Actually, this ambiguity is a lot more noticeable because ML can actually just ML just goes from minus L up to L. So we will have a lot more different eigenstates. And also MS is either 1/2 or minus 1/2. So we will have a lot of different states with the same energy. So all of these states would have the same energy. And now there will no longer be one state without energy, but rather a hell of a lot of states with the same energy. And this could be a problem in the future of derivation. In fact, we cannot use the same derivation for non-degenerate and degenerate perturbation theory because we get some singularities. So, well, this could be the outline of perturbation theory. I know that I repeated myself too much, maybe, in explaining these basic concepts, but it's just that I think that it's really important that you have these concepts really clear, and also that you get used to the notation. Also, just introducing some other notation. These eigenstates, in general, I will call them phi n sub I, 0. And this I just stands for the different eigenstates with the same energy. That is, as we said before, n is okay, this corresponds to the nth energy, this 0 corresponds to H naught, and this I just means that maybe we're dealing with this one, or this one, or this one, or so on. So this would be just for the general perturbation theory. Now let me just erase all of this, and we can actually get started with the general time-independent perturbation theory.